Advanced Electronic Forensics. Welcome to the casebook of Advanced Electronic Forensics, where every non-functional device is a puzzle waiting to be solved. The symptoms of the failure are the only initial leads, and the circuit board itself is the crime scene. Our mission is to meticulously reconstruct the chain of events by following the evidence to the point of failure. Stethoscope, the art of triage. Every investigation begins with triage, a preliminary examination conducted before any invasive measures are taken. This initial assessment is crucial because fleeting evidence, like heat or odor, must be captured before the scene is disturbed. These first observations form the foundation of a working hypothesis that guides the entire diagnostic process. Even for an expert, what is the first safety protocol you follow? The first principle of procedure is to verify the absence of energy, ensuring the device is disconnected and all capacitors are fully discharged. A large capacitor can hold a lethal charge long after being unplugged, acting as a hidden booby trap for the unwary investigator. This step is non-negotiable, as it guarantees a safe and controlled environment for the subsequent analysis. What are the subtle visual cues on a PCB that you look for? The board itself is a map of the crime, and the search is for physical anomalies left by electrical stress. A subtle discoloration of the printed circuit board, or PCB, for instance, points toward a component that has been chronically overheating. These are the fingerprints left behind by the physics of the failure, telling us where to look closer. Beyond the obvious smell of smoke, what can different scents tell you? Different failure modes produce distinct olfactory evidence that can guide an investigation. The sharp, acrid smell of a burnt resistor indicates a sudden, high-current event. A leaking capacitor's electrolyte, however, has a unique, fishy chemical odor, providing a clue that suggests a slower, degenerative failure. How do you use a thermal camera to quickly identify parasitic loads? A thermal camera provides immediate, non-contact evidence of improper energy dissipation. A component glowing brightly under no-load conditions is a clear anomaly, indicating an internal short is converting electrical energy directly into heat. This technique allows for the rapid localization of faults that would otherwise require painstaking point-by-point measurements. The diagnostic arsenal. With the initial observations complete, the primary investigative tools are brought to bear. The multimeter and oscilloscope are not mere measuring devices. They're instruments of interrogation that allow for direct questioning of the circuit. They translate the invisible world of electrons into hard data, forming the backbone of any solid diagnosis. Beyond standard voltage checks, what is a multimeter function pros use for deeper diagnostics? The relative measurement mode is a critical function for identifying subtle deviations that might otherwise be lost in the noise. By establishing a baseline from a known good component, the meter is instructed to display only the delta or deviation for all subsequent measurements. This makes minuscule but significant differences in component values immediately apparent. When you decide to put down the multimeter and grab the oscilloscope, a switch from the multimeter to the oscilloscope is warranted when the evidence suggests the fault is dynamic, not static. The multimeter provides a single, average data point, but the fault may be a transient spike or an unstable oscillation lasting only microseconds. The oscilloscope is the only tool that allows for the witnessing and analysis of these fleeting events over time. What is the first thing you look for on an oscilloscope when diagnosing a faulty switch mode power supply? The switching node is the first place to probe because its waveform is the most information-rich signal in a power supply. The integrity of this signal, its frequency, duty cycle, and clean edges, is a direct reflection of the health of the entire control circuit. Any distortion here immediately proves that the problem lies within the core power generation stage. How do you definitively differentiate between input noise and actual output ripple on the scope? AC coupling is used for the specific purpose of removing the large DC component of the voltage rail, which allows for the magnification of the tiny AC ripple signal. Engaging the 20 MHz bandwidth limit is also critical, as this action filters out unrelated high-frequency noise. This two-step process isolates the signal of interest, ensuring the measurement is of the power supply's actual performance. Can you share a trick for using a multimeter's frequency mode to check if a crystal is alive? A multimeter's frequency counter offers a quick, non-invasive test for signs of life in a crystal oscillator. The probe can often detect the faint electromagnetic field from the oscillating crystal via capacitive coupling. A stable frequency reading confirms the circuit's primary clock source. Its heartbeat is active, allowing the investigation to proceed downstream. If the oscillator is running, what's the next step to verify the microcontroller isn't stuck in a reset loop? Probing the microcontroller's reset pin reveals whether the processor is executing code or is trapped in a startup failure. A continuous train of pulses on this pin is hard evidence of a reset loop, where the system's watchdog timer is repeatedly restarting a failed processor. This confirms the processor has power but is unable to run, pointing to a fault in the core logic. A rogues gallery revisited. An examination of the usual suspects is the next logical step, as statistics show that certain components are predisposed to specific failure modes. An expert diagnostician, much like a seasoned detective, is intimately familiar with the methods of these common culprits. This knowledge allows for a more efficient allocation of time and resources. After replacing a blown fuse, what secondary damage do you immediately hunt for? A test for a low impedance path to ground must be performed after replacing a fuse, because the fuse itself is never the root cause. The fuse blows to protect the circuit from a component that has failed and created short. Finding and replacing that shorted component is the only way to permanently resolve the issue. When a MOSFET fails short, how do you determine if it was a gate driver failure or a thermal runaway? The gate drive signal must be analyzed to determine if the metal oxide semiconductor field effect transistor, or MOSFET, was commanded to fail or if it failed on its own. A distorted gate signal proves the driver circuit is the true culprit. A clean signal, however, exonerates the driver and indicates the MOSFET failed internally, likely due to thermal stress. How do you diagnose a voltage regulator that has poor load regulation or transient response? A regulator's true performance is assessed under dynamic load conditions, not static ones. Applying a rapidly changing load and observing the output voltage on a scope is the only way to verify its stability. Excessive voltage droop or overshoot under load is direct evidence of poor regulation. What is your go-to method for hunting down intermittent cold solder joints? Localized thermal and mechanical stress is the primary technique for finding intermittent faults. Using freeze spray or hot air changes the physical properties of the components in a controlled way. A sudden change in circuit behavior when a specific area is stressed is a direct confession from the faulty connection. How can a failing relay coil, not just the contacts, create bizarre symptoms? The relay's coil must be investigated because its magnetic field is the prime mover for the mechanical switch. A partial short in the coil can create a weak or unstable magnetic field, leading to chattering or high-resistance contacts. This is a deceptive fault, where the control mechanism itself, not the switch, is the source of the problem. How do you effectively test an optocoupler when you suspect it is failing to isolate? An optocoupler is tested as two distinct components to verify its primary function, galvanic isolation. The test must confirm that a signal passes via light from input to output, and also that no electrical connection exists between them. A low impedance reading between the two sides indicates a catastrophic failure of the isolation barrier. What are the signs that a multi-layer ceramic capacitor has failed? A dead short on a power rail often points to a failed multi-layer ceramic capacitor, or MLCC, as this is their most common failure mode. The failure is a microscopic internal short, leaving no external trace. This knowledge allows for a clear hypothesis when faced with an otherwise inexplicable short circuit. Needle: how can a shorted ceramic cap on a main power rail be the ultimate needle in a haystack? Thermal imaging combined with voltage injection is the definitive method for locating a single shorted MLCC among dozens of identical components. Injecting a limited current forces the shorted component to dissipate that energy as heat. The thermal camera then makes this anomaly visible, instantly revealing the culprit's location. The capacitor plague. A deeper analysis of the physics of capacitor failure is necessary because the visible evidence is merely the final symptom. Understanding the degradation of electrical parameters like ESR and ESL is key to true root cause analysis. This allows for not only fixing the failure, but understanding precisely why it happened. How does elevated ESR on a smoothing capacitor manifest as a visible fault on an oscilloscope? Excessive AC ripple on a DC output is direct evidence of high equivalent series resistance, or ESR. A capacitor with high internal resistance cannot effectively shunt AC noise to ground, so the noise remains on the voltage rail. This ripple is a key piece of evidence that the power supply's filtering stage is compromised. What is your rule of thumb for an acceptable ESR value for a given capacitor in a power supply? The formula 1/2 asterisk pi asterisk F asterisk C is used to establish a baseline for maximum acceptable ESR because a capacitor's effectiveness is frequency dependent. The ESR must be significantly lower than the capacitive reactance at the operating frequency for the component to perform its filtering function. This calculation provides a quantitative, evidence-based threshold for judging a component's health. What does the dissipation factor, or tan delta, tell you about a capacitor's health? The dissipation factor is measured because it directly quantifies the capacitor's inefficiency. This value reveals how much stored energy is being wasted as heat within the component due to dielectric losses. A high dissipation factor is the signature of a dying dielectric, a warning that the component is approaching the end of its operational life. How can a capacitor with a perfect capacitance value still be useless in a high-frequency circuit? Equivalent series inductance, or ESL, must be considered because at high frequencies, this parasitic inductance can dominate a capacitor's behavior. This ESL creates an impedance that rises with frequency, which can render the capacitor useless for high-speed decoupling. This explains the paradox of a component that tests good for capacitance, but fails to perform its function in the circuit. Can you give an analogy for why a capacitor's equivalent series inductance is so critical? The component's ESL represents its inherent inertia, its inability to respond to instantaneous demands for current. In high-speed digital circuits, processors demand that current instantly, and the capacitor is meant to be a local, fast-reacting reservoir. The ESL introduces a delay in the supply of that current, which can be sufficient to cause data errors or system crashes. Advanced field techniques. Advanced field techniques are required when standard procedure is insufficient. These are specialized investigative strategies designed to extract information from uncooperative circuits. They are essential for solving cases where the evidence is hidden, misleading, or seemingly non-existent. How do you use a bench power supply with current limiting to safely locate a dead short? Injecting a known amount of energy into a shorted circuit is done to observe the fault without causing a cascade failure. A bench supply set to a low voltage and a strict current limit creates a controlled fault condition that is safe to analyze. This method forces the shorted component to reveal itself by dissipating the limited current as heat. What is your favorite technique for tracing a signal on a multi-layer board without a schematic? Manual reverse engineering of the circuit is the only option when a schematic is not available. Tracing the physical connections reconstructs a portion of the designer's plan. This allows for the formation of a testable hypothesis about the circuit's function, which is impossible without knowing how the components are interconnected. Can you explain the concept of component signature analysis? Signature analysis is used because the voltage current response of a component is a unique and unalterable fingerprint. Applying a known AC signal and observing the resulting VI curve allows for the identification of a component without removing it from the circuit. Any deviation from its known signature is conclusive proof of a fault. Without a dedicated curve tracer, how can you approximate this technique with a scope? A simple octopus curve tracer can be built to make signature analysis accessible, because the principle is more important than the tool. This device allows the oscilloscope to plot the voltage current signature, providing the same fundamental diagnostic capability as a dedicated curve tracer. It demonstrates that a deep understanding of theory can often overcome a lack of specialized equipment. When do you finally resort to destructive testing, like lifting an IC pin? Destructive analysis, like lifting an IC pin, is a last resort, warranted only when a testable hypothesis can be proven by isolation. If an integrated circuit, or IC, is suspected of corrupting a shared data bus, temporarily severing its connection is the only way to confirm its guilt. It is a calculated risk, taken only when the potential for a definitive answer outweighs the cost. How do you use schematics to understand the original designer's intent? The schematic is studied to understand the designer's intent because a failure is often a deviation from that original intent. Analyzing the circuit topology and component choices reveals the intended performance characteristics. This allows for the recognition of when a component has failed not just electrically, but functionally within the designer's plan. The grand strategy. The final element is not a tool, but a mindset, the grand strategy. This is a systematic and logical approach to problem solving that ensures no clue is missed and no assumption is left unchecked. This disciplined process is what allows an expert to solve any puzzle, no matter how complex. How do you develop a mental model of a circuit's operation before you even start measuring? A mental model of the circuit's function must be constructed before testing, because measurements without a hypothesis are merely data points. By understanding the intended function of each circuit block, one can predict the correct behavior. A measurement then becomes an experiment to confirm or refute the model, a far more efficient process than random probing. Not Sun, can you walk us through your thought process when confronting a completely unfamiliar piece of equipment? Confronted with an unfamiliar device, the first priority is to map its power entry and distribution network, as no circuit can function without a stable power source. The next logical step is locating the primary controller, which tells you where the intelligence of the system resides. Finally, identifying the main inputs and outputs reveals the device's fundamental purpose and completes the initial high-level assessment. What's your strategy for faults that only appear under specific thermal conditions? Localized thermal stress is used because temperature-sensitive faults are caused by microscopic material changes that only manifest at specific temperatures. Applying freeze spray or hot air forces the component to enter its failure state in a controlled manner. This allows the fault to be witnessed on demand, which is necessary to prove which component is responsible. How do you differentiate between a simple component failure and a fundamental design flaw? A distinction between a failure and a flaw is made by looking for patterns. A random component failure is a statistical anomaly, but a design flaw is a systemic weakness that will cause the same failure repeatedly. Evidence of a design flaw is seeing a component operating outside its specified limits or finding the same fault across multiple identical units. What is the most counterintuitive or surprising solution you've ever found for a complex problem? The solution for a complex audio amplifier hum was once traced to a single loose screw, creating an intermittent ground. This was a mechanical, not an electronic, problem, but it produced a cascade of bizarre electronic symptoms. It was a powerful lesson that the root cause is often not what the initial evidence suggests, and one must not get tunnel vision. After a repair, what final verification steps do you take to ensure its long-term reliability? Final verification under full operational load is required to ensure the repair is robust. A circuit can appear stable under light load, but the true test is its ability to perform its function under the maximum stress for which it was designed. This step is critical to confirm that the device has been restored to its full operational capability. What is soak testing, and why is it a critical final step for intermittent repairs? Soak testing is employed to expose latent or thermally induced failures that would not appear in a short-term test. Running the device for an extended period allows all components to reach thermal equilibrium, which can reveal weaknesses that only manifest over time. This is the final step to ensure the repair is not just correct, but reliable.